Assalamu alaikum wa rahmatullahi wa barakatuhu. Dear students, today we are going to take a new turn from our course that we have a three section of our physical chemistry three courses. So the first section is electrochemistry, the second is quantum mechanics, and the third one is spectroscopy. By the grace of Almighty Allah, we had completed the first section, and I'm really proud of all of you that you take a lot of interest in understanding, learning, and practical implementation in some cases of that courses. And there was a regular contact of a lot of students from that sixth section, that is BS sixth, either A class or B class. So I really proud all of you. Okay, today we are starting to study the quantum mechanics, but today is just an introductory lecture. So there must be a lot of question in your mind that what is classical mechanics and what is quantum mechanics. So the first question is, what is classical mechanics in your mind? I will try to solve this question, resolve some of the issues regarding classical mechanics in this class. The second one, what is quantum mechanics? If there is quantum mechanics, if there is classical mechanics, so why we need quantum mechanics? Classical mechanics is also known as Newtonian mechanics. Now, which people will never need quantum mechanics? There are some people in the world that throughout their entire lifespan they never need quantum mechanics. And why we need quantum mechanics? Why? What is the need of quantum mechanics? And what are the backgrounds that led to the invention of quantum mechanics? And why is quantum mechanics so different and difficult? Okay, there are some metaphors, perceptions, rumors, and a lot of speculations from different people regarding this last point, that I never agree with this term, that most of the people think that quantum mechanics is a terrible subject, is a terrifying subject. They are not understandable subject. It's a really amazing subject. It's really very interesting, and all the points in quantum mechanics, a normal human body can really understand that, and they can really implement that in their life. So please don't worry about that quantum mechanics is a little difficult, or the rules formulas are not understandable, the terminologies are technical. No, there is nothing like that. By the grace of Allah Almighty, we will try to solve all these questions that I have mentioned over here. Now, slowly and gradually, we can move. But before starting any issues, I will try to explain some things from the very beginning. They try to focus at what I am saying over here. If your mind is diverting from time to time, and you are physically somewhere, mentally somewhere else, then it's really very hard to grasp all the subjects that we are going to study. Okay, now these are the pioneers, these are the true names, and these are the pioneers of the quantum mechanics. The first name that is very famous, that is Erwin Schrödinger, that the whole base of quantum mechanics is based upon on his equation. And that equation is, maybe some of you still remember and some of you don't remember, that h psi, if you remember, that will equal to e psi. That is his equation. Okay, this time I don't want to disturb all of you just by writing that. So just keep in mind that there are two pioneer persons, Erwin Schrödinger and Werner Heisenberg. These two pioneer and very famous scientists, they laid the foundation of that very interesting and a very amazing subject, that is the quantum mechanics. Okay, slowly and gradually go. Now, classical mechanics, the world we are living, that we are eating, we are moving, we are walking, we are playing, or whatever these different circumstances, these are just, we are living in a classical world, and all these mechanics are explained by Newtonian mechanics. For example, if an object is moving, is okay, there is no problem. A car is moving from one place to another place at a distance of 100 kilometer, and the car is running with the 120 kilometer per hour. So the Newtonian mechanics can easily explain that. Now, if you are forcing an object, then what happened to the motion of that object? There is acceleration as a result of that applied force. So what is the relation between that applied force? If, for example, if there is a body of there is a space shuttle ejecting from the space from this our globe world and going to any other place, for example, to the moon or to some other places outside that our globe. So that all these phenomena was easily explained by classical mechanics. There is no problem at all. Like in these different examples, there is a space shuttle coming out of our Earth. So, is it possible that Newtonian mechanics can explain that? Yes, of course, it can explain that. There is no problem at all with that. Then why we need that classical mechanic? Why the classical mechanic fails? Okay, classical mechanics they are known for centuries. They are Newtonian mechanics in 1687. Okay, but after some time, there is some addition, or you can call them there is some upgradation by Lagrangian mechanics, Hamiltonian, like that is 1788. And then there is addition by Hamiltonian mechanics. Luckily, there is also use of Hamiltonian mechanics in in quantum mechanics as well. Now there is also addition by Boltzmann. Maybe you remember the name. Is some people afraid of the names? Don't afraid of the names. These are also human beings, and their work is really acknowledged by all scientific community. There is Boltzmann's entropy equations. So all these are dealing in the classical mechanics. There is no problem at all. Okay, but in the start of 1920, when there was 1920, there was some vacuum created or a vacuum due to the quantum mechanics. Okay, I will not say vacuum due to quantum mechanics, vacuum created in the classical mechanics that was not filled by the classical mechanics. So that vacuum was replaced by quantum mechanics. Okay, now what does this quantum mechanics means? The first thing, what was that vacuum? There are two basic points. The first point that I will try to, you should remember that the first point, that whenever we are studying any object and the object of that, the size of that object is large enough. Now, large and small, these are two relative terms. Now, what is large, what is small? Okay, I will say if the size is more than nanometer, then classical mechanics can easily explain that. The second point, if that body is moving with the speed of a car or the speed of aeroplane or bullet train or whatever the case may be, but that is not comparable to the speed of light that we represented by c. And I think that all of you remember that the speed of light is 2.9 into 10 raised to power 8 meter per second per second. Okay, that is the speed of light. So if the speed of that object is not comparable to the speed of light, then classical mechanics works. But if the speed of light is comparable to the speed of light, if the speed of any object is comparable to the speed of light, then the classical mechanics fail to explain the phenomena. So there are two scenarios. The first one, the size. There is a size problem. If the size is below narrow range, then classical fails. Now, if the speed increases and reach up to the speed of c, that is speed of light, then classical mechanic fails. These are the two basic things. If you just remember these two, then I'm sure that all the rest of the points will be explained very easily. Okay, now first of all, what is this word quantum means? So quantum is basically a unit, that is the smallest thing, smallest possible amount. Now, for example, if you take the radiations, so radiations, it was also explained by in the start of 1920s that radiation is nothing but these are in the form of photons, small packets, and these packets are photons. No matter that these are blue radiation or these are red radiation or these are green radiation, whatever the light may be, what does basically it indicates? It indicates that either this is a high energy radiation or low energy radiation. No matter either it is high energy radiation or low energy radiation, it is just the composition of small packets of energy, and these are called photons. So again, there is a unit, and that unit is called photon. So that is the smallest one. Now the second one, if you take any of the charged particles, so there is a positive charge particle and there is a negative charge particles. So positive charge particle, for example, in our modern world, we can easily understand that there is a proton and there is a negative charge, that is electron, but still there is a positive and there is a negative one. So it means that there is a unit for everything, even for radiations and even for charge and even for everything. So whenever we are discussing anything, we need some units, and that unit is quantum or quanta. That is why the quantum mechanics just arrives from the very basics. Now, quantum mechanics is can explain all the phenomena of motions, no matter of the small objects or large objects, very easily, and all the prediction. There is no one that has ever found any predictions of quantum mechanics to be wrong. And the reason behind this is, if you just remember that quantum mechanics can deal with the very small objects. So if some rules regulation are accurate at a very low level or a very minor level, then it's really hard to fail that laws at a larger scale. So that's the reason and that's the logic. But quantum mechanics applies equally well for small things. If you think that is it possible that we can apply or implement the rules of quantum mechanics on larger objects, of course you can implement, and you can also implement that on smaller objects. Smaller objects mean electron, proton, positron, and then even quarks that I will discuss later on. Okay, so but it would be foolish to use quantum mechanics where classical mechanics is good enough. Okay, now the reason behind that is, if classical mechanics works somewhere in our daily life, then we don't need quantum mechanics. But if classical mechanics fails, then we use quantum mechanics. Okay, for example, I will give you some examples. Now, if you just remember my two statement, the first one is the very smaller size, and that size is up to the nano range, below nano range, then classical fails. The second point, the speed of light, comparable to the speed or speed of light. Nobody can exceed that, but okay, we can just comparable. If that is 10 raised to the power 7 meter per second is also okay. Now, there is a mechanics. Now, this mechanics do not need classic quantum mechanics. Why? It's very easy to answer, that anyone can answer this question, because whatever he is dealing here, these are bigger objects and one can even see with their naked eyes. So there is no problem. He is dealing with the classical objects, so he need only classical mechanics. Now, this person, electrician, who is just playing with the wires, that is electrical wires. Now, he's dealing with that, but he don't need quantum mechanics to do that. Why? The reason behind that is, he is dealing with objects, and that objects is large enough. If there is amount of electricity, now electricity is not so small. Okay, let's suppose, for the sake of simplicity, I will give you the example. If there is only one electron coming after even 5 minutes, 6 minutes, then of course he need quantum mechanics. But that's not the case. So when that is not the case, then he don't need that. Electrician do not need quantum mechanics. Okay, now, okay, let's proceed further. Now, doctors also don't need quantum mechanics. Okay, that's a little bit tricky over here, but just for the sake of simplicity over here, I will mention here that doctors don't need quantum mechanics because, okay, uh, the field where they are going to practice is starting from where? Let's say just from the birth of a child till the death. Okay, so during these scenario, that is this we are started from one, we have just put a limit. Like for example, we have integration, so we put a limit here, and we have put a limit over here. So I just put a limit over here, that is birth, and here I put a limit, death. So doctor is dealing from this birth till death. Okay, this regime, and he is dealing the human bodies with the he is dealing with the human bodies. So he's not dealing with the quantum mechanical objects. So when he's not dealing with the quantum mechanical objects, so he don't need quantum mechanics. Classical mechanics can work in that range, so that is why he don't need that. Okay, now just coming toward the scientist. Okay, biotechnology is one of the emerging fields. Just for your information, bio means, I think all of you sure about that, living and technology. If you are using any biological specimen for technological purposes, like these days you see that there are different breedings, hybrid breedings, and there are cloning and so many other technical terms over here. So most of them are dealing with the classical objects, so that is why they don't need quantum mechanics. Okay, there are also some field of physics they don't need quantum mechanics. For example, plasma physics. So plasma physics, they also don't need quantum mechanics. Okay, so when do you actually need quantum mechanics? That's the question in your mind. Now, what we had discussed till now, so if you just draw a borderline, that where we can use quantum mechanics and where you cannot use quantum mechanics. So I told you that there are only two rules till now that I have discussed. The first one is regarding the size. If the size is large enough, then it's okay, then you don't need. If the size is small enough, then of course you need to use the quantum mechanics. Okay, so that is the first one is the size, and the second one is the speed. Okay, now regarding the speed, I have a restriction over here that the speed and the size, both of them should be not, you cannot take it as a normal. This may be comparable to that. For the sake of simplicity, I will write 3 into 10 raised to power 8. That is meter per second. And the second one, size, is, let's suppose you take, I take for the sake of simplicity angstrom. So if there is an object in the angstrom range, then of course your classical mechanics fails. And then what you need? Basically, you need quantum mechanics. You need to use quantum mechanics. Okay. So that is the simple logic. Later on, I will explain some of the other term as well. Okay. Now the first one, what about size? I told you that for small things, small object you can use, but how small? Okay. For example, you take like an elephant. Elephant is a small or big, so maybe it's very big, but it is small for some other object as well. Okay, let's suppose we are taking some other, like that's a paper pen. If you compare that with that elephant, now of course it's very small, but if you compare that paper pen with a cell, then of course there is a big difference, because that's almost 1 millimeter, but that is a micrometer. So there is almost uh, 10 raised to power 3, 1000 times difference between both of them. Okay. Now, if you take a cell that is a very general cell, okay, that's not as very specific. So don't be very specific over here. So if that is a general cell and that is a molecule, okay. Now this molecule is almost in the range of 1 nanometer. So when this molecule is in the range of 1 nanometer and the cell is micrometer, so how much is the difference? There are almost 10,000 times difference between both of them. So due to this big difference, now all these materials, what we had discussed, is classical one. So when they are classical one, can we use a quantum mechanics? Of course, no, you cannot use. You don't need to. You can use, but you don't need to use that. Okay, that is will be a foolish act if you are using a quantum mechanics in that range. Now, what about this one? Is somewhat non-classical, this compound. Okay, so here you can try the classical mechanics. You can to use a quantum mechanics instead of classical mechanics. Okay, let's move further. Okay, now big and small, we can take a comparison now. Head of a pen, how much it is? It's almost how much nanometer is 1000 nanometer. Okay, now what about this an object that is a pollen grain? So that is a 20 micrometers. It's almost a 20 micrometers or 20,000 nanometer. Okay, so that is 20,000 nanometer. Okay, you can just compare the sizes now. What about this one? That is a red blood cells. I'm sure that all of you know about this RBCs. What is the size of RBC? Is almost 2500, 2500 nanometer is almost in the same this range. Okay, what about carbon nanorod or carbon nanotube? So that is a 2 nanometer. So that is, now we are just moving from larger objects toward a smaller one. Now over here, if I just draw a line over here, here you can use classical mechanics, but here you cannot use classical mechanics in that range. So that is just the difference over here, that how much small and how much large. Okay, now quantum mechanics is absolutely essential for understanding atoms and their properties. Okay, why? Because I told you that the size of the atom is almost in the range of 10 raised to the power minus 10 meter, and you know this is almost angstrom. So we are at the regime of smaller size in the range of quantum mechanical objects. So whenever we are studying, what about this size now? The nucleus. And what about size of the electron? So if you just compare both of them, of course you cannot explain them by classical mechanics, so you need now quantum mechanics. So these are just the comparison between a smaller and larger objects. Okay, okay, let's just go into the details. Size of the atom, I told you, is in the range of almost 10 raised to power minus 8 centimeter. And you know 10 raised to power minus 8 centimeter is almost equal to, is exactly equal to 10 raised to power minus 10 meter, and 10 raised to power minus 10 meter is equal to 1 angstrom. Okay, So if there is 1 angstrom, I don't know, the pen is not working. Let me try it again. Okay. So if it is, so it means it's very simple that if anybody asks you about the general size of the atom, so you can just answer him it is angstrom range. Okay. Now if you just compare size of the nucleus to the size of the atom, now it is almost 10,000 times smaller than that of the atom. If you just compare size of the atom, that is the nucleus, and that is size of the atom. So size of the atom is 10,000 times greater than that of the nucleus. Our nucleus is 10,000 times smaller than that of the atom. Okay. So now you can understand this. We are going downsizing. Now what's downsizing? What's the proton? So proton is 10 raised to power minus 13 centimeter. Okay, it's much more smaller than that of the nucleus. Okay, but if you just look at electron size, so electron size 10 raised to power minus 16. So 10 raised to power minus 16, again it is almost, it is exactly 10,000 times smaller than that of the nucleus. So nucleus is 10,000 times smaller than that of the atom, and electron is smaller than that. Now, whenever, and of course, inside the nucleus, you know that if you just take the nucleus, there are protons inside and neutrons, and inside there are also quarks, and quarks is the size of 10 raised to power minus 16. Minus 16 means 10,000 times smaller than that of a nucleus. So now at this level you cannot use, of course at this time we cannot go inside that quarks and can find out what is inside that. But inside that nucleus we know that there are protons and there are neutrons and there are some other objects as well. Some of them are well defined, some of them are not well defined, but of course up to some extent we can explain the phenomena. Okay, so beyond this limit, now here, if you are just explaining something inside the nucleus, it's really very hard to explain on the basis of classical mechanics. You must explain on the basis of quantum mechanics. So that is why quantum mechanics is very important. Okay, let's move on. And maybe some of the students will get confused that quantum mechanics can only explain what is inside the nucleus. They cannot explain what is outside nucleus. No, of course not. Quantum mechanics, they can also explain a lot of phenomena like the state of matter, why this is solid, why this is gas, and why this is liquid. Because what is solid made of? It is made of some compound. For example, if we take the water, so it's again a water molecule. How the water molecule, that there is a bond formation between oxygen and hydrogen, how it forms? Of course, classical mechanics cannot explain that. Now, whenever it's just gather around, they form a hexagonal structure, a crystal, how it forms. Then gaseous form, and then the liquid form. So these different states of matter are beautifully explained by the quantum mechanics. Okay, quantum mechanics have a lot of manipulation on the electronics these well. Without quantum mechanics, so of course the condensed matter physics that these days we know that there are a lot of chips for computers and mobile phones, and there are a lot of resistors, diodes, and capacitor, and some microchips. So without a quantum mechanics, it's impossible to design such kind of small microchips for mobile or computers. So there is a lot of use of quantum mechanics on their side as well. Okay, now this is a wonderful graphene nanotubes. Is almost, keep in mind this nanotube is almost 1,000 times stronger than that of steel. Oh, so this time you will get confused. How is possible? Steel is a very strong enough, and carbon is a very rough and very delicate as well. But just believe me, this is a much more stronger than, almost 100 times stronger than that of steel. But for explaining this, is it possible that you can explain by classical mechanics? No, it cannot be explained. For this, you need quantum mechanics. Okay, so all these nanoparticles. Okay, just for the sake of simplicity, I will try to explain that nanoparticles a little bit more. Sometimes most of the student they ask this question that nanotechnology is totally based on the quantum mechanics. So what is nanotechnology? So keep in mind, okay, let me just find out a slide where I can write something for all of you. Okay, I will try here. Okay, so here let me explain this. Okay, there are some objects that size is smaller than that of nano range. Okay, it's and the range may be in x-axis, or maybe in the y-axis, or maybe in the z-axis. Okay, these are the three ranges. Let's suppose x-axis, and that is y-axis and z-axis. Okay, now if there is any object whose size is in the x-axis, y-axis or z-axis in the 10 raised to the power minus 9 meter range. We call them nano object or nanomaterial. Okay, so it may be possible that we have some object whose only along x-axis the size is in the nano range. Is it okay? Yes, of course, it's also okay. It may be possible, and we call that kind of object 1D nanomaterial, one dimensional nanomaterial. And there are some objects whose size is along x-axis and along y-axis in the nano range. We call them 2D nanomaterial. And that 2D nanomaterial, I will give you the example later on. And there are some objects whose along x-axis, y-axis, and z-axis, they are in the nano range, and we call them 3D nanomaterial. Okay. Now, the example of that 1D nanomaterial is nanorods. We call them nanorods or nanotubes. And that is one of the carbon nanorod is one of the example of 1D nanomaterial, carbon nanorods. Now, 2D nanomaterial, we call them nanosheets. Nanosheets. SH. Okay. Nanosheets are like that, and they are expanding like, but they are thin enough that this that size we can just by atomic force microscopy we can find out the witness of that. It's almost in the nano range. So no matter the other size is in more than that, but the two x and y are in the nano range. And there are some objects who are x, y, and z. All these x-axis, y-axis, and z-axis are in the nano range. We call them 3D, and we call them nanocrystal. Okay, nano crystals. Okay. Now these nanocrystals are of different shapes. Okay, some may be cubes, and I think you should know about this that there are some cubes, and there are different geometric shapes. Some may be octahedral, decahedral, icosahedral. Some have 20 faces, 10 faces. So these are so all these nanotechnological terms, that is 1D, 2D, 3D nanomaterials, their phenomena, the all the physical and chemical phenomena were only explained by quantum mechanics. Is not explainable by classical mechanics. So basically, I'm sure that now you have some ideas that nanomaterial is all that kind of material whose size lies in the range of 10 raised to power minus 9 nanometer, no matter x-axis, y-axis, or z-axis. So that is very important. Okay, that is one term that you should keep in mind. Now, no matter only if x-axis is in the nano range, we also call them nanomaterial. If x and y is in the nano range, also call them nanomaterial. X, y, and z is in nano range, we also call them nanomaterial. So these are just the simple explanation for that. Okay, but the difference between them is 1D nanomaterial for x-axis, 2D nanomaterial, and 3D. And for 1D nanomaterial, I have the example of nanorods, nanotubes. For 2D, we have nanosheets, and for 3D, we call them nanocrystals. Okay, let's move on. There are nuclear physics. So nuclear physics basically deal us the phenomena which are happening inside the nucleus. The disintegration or integration, there are some particles that are colliding with one another, and as a result of that, nuclear fission or fusion reactions. So these are different phenomena that we are studying inside the nucleus in the nuclear physics, and most of these phenomena were explained by quantum mechanics. Now these radiations are used also for radiotherapy as well, and also for some other purposes like cancer treatment. There are a lot of hospitals in the world, they are treating cancers just by radiation. We call them radiotherapy. And we are also using that kind of radiation for production of energy. So it means that the implementation and practical usage of that quantum mechanics is not a limited one, it's unlimited. But the basic need is to understand it clearly. Okay, there are also some nuclear medicine as well that are made, and I told you that these medicine basically they work on that principle, that there is some fission or fusion reaction inside the nucleus, and they follow the rules of quantum mechanics. And when they follow the rules of quantum mechanics, automatically they are in the regime of quantum mechanics range. Okay, now quantum mechanics is need for understanding the early moments of the universe just after the big bang as well, that what happened. But I will not go to the details of that now. It's not at this state. I will explain these phenomena later on after 5 6 lectures, then you can understand all this very clearly. Okay, now how quantum mechanics begins, that's a very interesting story over here. because in the early 19th centuries, physics, chemistry, all the science are quite mature enough. For example, the rules, the conservation of matter and energy, uh, there was a well established fact regarding that mass remain constant and energy remain constant. You can convert into mass can convert into energy, but the total amount, both of them, is remain constant. Wave nature of light, there were a lot of experiments who clearly prove that the nature of light is wave nature. Okay, and some of the scientists, they also explain that it is electromagnetic in nature. Okay, uh, and the nature of heat is a random motion, because there are atoms colliding with one another, and there is random motion, and due to that random motion there is a collision, and as a result of that collision there is a heat. So there are a lot of prediction and discovery regarding radiations, regarding heat, and some X-ray phenomena. They also discovered that there is electron, and there is also in the atom there is proton in the atom. They also find out that there are some sort of radiation that can pass through the human bodies, like X-rays radiations. So these are the discoveries, but still there are some serious puzzles in the science that scientists were unable to explain. That is why they need a quantum mechanics. And what are these puzzles? Okay, let's take one by one. The first one, when atom absorb energy or emit, they are just at particular frequencies. Why it's so? Why hydrogen absorb spectra like that? So hydrogen emission spectra, and that is a absorption spectra, why it is like quantized. So this is a strong hit that atom have quantized energy. Is not possible that they can cross, or there is a continuous type of spectra. So this quantization was one of the clue, or this particular frequency of light emission or light absorption by hydrogen atom was one of the clue towards the opening of the quantum mechanics. That was the first one. Okay, the second point, okay, let's look over here. If there is an atom and that electron is revolving around that, now we know that there is a positive charge over here and they carry a negative charge over there. So after some time it must fall down in the nucleus, but it never happened. Why does the electron fall into the nucleus? Electron do not fall into the nucleus. Why? There is no explanation in the classical mechanics for that. So that is why it's also the birth of the quantum mechanics as well. Okay, the third one, that is, why don't atoms disintegrate on collision when atoms are colliding with one another? Why they don't disintegrate? It never happens. So when it never happens, it was not explained by the classical mechanics. So that is why we need a quantum mechanics as well. Okay, the third puzzle is very interesting, that the structure of the atom, for example, if we take the first, this column, so all the elements have similar chemical properties. And here it also have the similar chemical properties. Now, if you take any of the column, they have similar properties. Why? So the classical mechanics do not have the answer for that. Why? And that's the reason that we need a quantum mechanics, that quantum mechanics can easily explain that. Okay, now, okay, this is also very interesting, that why there is a chemical bond between the atoms, why hydrogen can make a bond with a hydrogen, and why there are certain elements they can make bond with certain other elements but cannot make certain bonds with some elements. There are some restriction rules as well. Like you can see here, hydrogen can make bond with oxygen. Hydrogen can also make bond with itself. Why? So there is no answer in the classical mechanics for that. So that is why we need quantum mechanics. Okay, that's very interesting over here. If we just heat a body, now after the heating, what will happen? You can look over here, when we increasing the heat, like previously we have a 3000 Kelvin. So if the temperature get increased, now the wavelength is shifting towards the left hand side. Now, why it's shifting toward left hand side? It means that as the temperature or as the energy increases, that the wavelength decreases, frequency increases. Why? Again, it was not explained by the classical physics or classical mechanics. So that is totally different. Okay, let me show you this now. Now this is the classical explanation. Okay, classical theory experiment, but the experimental one was this one. As I told you, that as the heat intensity of the radiation increases, the wavelength is shifting toward a narrow range. So as we know that the wavelength and the frequency, they have inverse relation with one another. So whenever this goes towards a narrow range, this will get increased. So the frequency increases. But why? So there was no explanation in the classical physics for that. So that was the reason that we need a quantum mechanics to explain that. Okay. Okay, quantum mechanics require making a certain logical mathematical postulates or assumptions. Okay, and I told you in the very beginning that the Newton formulas or Newton rules have a very peculiar role in the classical mechanics. Same is for Schrödinger wave equation. Now, these led to the physical consequences which are weird outside our daily experience. For example, I will just tell you one example, then I will try to finish this lecture. The first thing, okay, that is that is a weird fact. A quantum particle are delocalized, meaning we cannot have well specified position in quantum. Classically, if there is an object over here, it will be located at this position. But in case of quantum mechanics, whenever there is an object, we cannot say exactly that the object is located over here. It may be over here, it may be some over here, it may be over here, it may be. We can just specify some range that inside that range there is a probability of finding that particle, and we call them the psi. That is a wave function. Wave function can explain that. Then wave function just then we take the probability of that, then the square. Then we can find out that inside that range there is a probability. So in the classical mechanics, we can easily explain the nature that if object is present over here, the position is well specified. But in the quantum mechanics, is not well specified. There is only probability. Some region, for example, if there is, I just mentioned this region. So here is the probability is maximum, is okay, no problem. If the probability here is minimum, is okay, but we cannot see exactly the particle is here, exactly the particle is here. So that is a weird fact of the quantum mechanics. Okay, there is another weird fact. There is a Heisenberg uncertainty principle. In a classical mechanics, you can determine both the position and velocity of any body. Okay, but that's not true for quantum mechanical objects. Why? Why it's not true? For example, that is an electron. And when you shoot that electron with some of the radiation, so that a photon, so the photon changes the position of that electron. So when it changes the position, so you can find out its velocity changes, but you cannot find the position. So there is a rules that delta x cross delta p. If there is uncertainty in the position, there is certainty in the momentum. If there is uncertainty in the momentum, there is certainty in the position. Both of them you cannot find simultaneously. So that things just happen in the quantum mechanical objects, not in the classical objects. Okay, that is also a weird fact over here. Now, what is Heisenberg uncertainty principle? Heisenberg uncertainty principle that the product of uncertainty in the position and in the momentum is equal to, or they are almost greater than that of h cross over 2. Okay, and what is this h cross? That is h over 2 pi. Okay, and that you have already studied these kind of explanations in your previous classes, so that is why I don't want to take much time over here. Okay, now there is a particle can behave either a particle or wave. Okay, in the classical mechanics, it may be a particle or it may be a wave. In quantum mechanics, it acts as a particle or it acts as a wave. At the same time, it acts as a wave. At the same time, it acts a particle nature. So there is a dual nature of particle, a dual nature of light. So these things, these are the weird facts. Like there is another weird fact. The extern Gauss-like experiment, they just heated as silver particles, and when they pass through a non-uniform magnetic field, so apparently it seems to be that it will strike over here, but some of the particles strike over here, some of the particles strike over here, and the intensity is shown here, and here there is no chances or possibility of over here. What does it mean? This suggests that there is a quantized angular momentum of these particles. So these are the certain weird facts that were not explained by classical mechanics. Okay, there is another very funny examples over here. For example, if you just kick this ball and the amount of energy they just reach over here. Now, it don't have enough energy to cross this barrier. What will happen? It will again come back. Okay, it will not climb. Now, that is a classical quantum mechanic. What does it explain? It may be possible that you kick this with certain amount of energy, it cross this and can reach over here. Oh, it's a really weird fact. So, and that's called quantum tunneling. So that are the weird facts that a normal person and some people's really they get confused over here. But when you go to the details of that, there is a certain explanation for everything. So here it tunnels through the hell despite of insufficient energy. So it goes like this. So these are the things that will be explained in the quantum mechanics. The other things that is more important, that let's suppose at time t1 there is an object placed over here, and you are expecting that after some time it will be here. No, it's not possible in the quantum mechanics. It may be here or it may be here. So time has a major factor over there, because psi that I told you, that is a wave function. It is a function of x and t. If this changes, psi changes. If t changes, psi changes. So these are the certain weird facts, but there is some reason for everything, and there is some reason that can explain the basic phenomena. And the basic reason for all these things is your understanding, your grooming, and your concentration is toward the real understanding of this world. Okay, we will continue this discussion. I hope you will enjoy a lot this journey of the quantum mechanics. And don't be discouraged, don't be dishonest, and don't be disheartened. Be loyal to yourself, be safe, sound, and give your time. It is a quality time to your study. And thanks a lot for listening. Assalamu alaikum wa rahmatullahi wa barakatuh.